In this unit, we're going to learn how to assemble a law of mass action, which allows us to quantify the concentrations of our products and reactants in an equilibrium reaction. The objective of this unit is to understand how to assemble that and how we use those numbers, but also to see what happens when we have multiple reactions. How do we assemble the law of mass action or quantify that equilibrium constant for this new combination of reactions? So when we're looking at a law of mass action, it's based on a balanced chemical equation. Like many of the things we've seen in chemistry, we want to look at a balanced reaction. Now notice that K values do not have any units. Equilibrium constants do not have a unit associated with them. So what we're looking at here is we start with our balanced reaction where we have A moles of substance A, B moles of substance B, going to C moles of substance C, and D moles of substance D. When I'm writing my law of mass action, what I'm going to look at is the amount of products, the concentrations of products raised to the power that equals their coefficient, divided by the concentrations of the reactants raised to their coefficient as their power. So here in this reaction, I get the concentration of substance C to the C power, the concentration of substance D to the D power, the concentration of substance A to the A power, and the concentration of substance B to the B power. Now I have a general formula for assembling these law of mass actions. So what we want to do is look at a specific example for a different reaction. So what I can look at here is I have a balanced equation, 2 hydrogen plus oxygen yields 2 water. And note that we are looking at these all in the gas phase. We'll talk in just a second about how we deal when we don't have everything in the gas phase. Here we're looking at water as our product, and I raise it to the second power because my coefficient is 2. On the denominator, I have hydrogen as a reactant, again, raised to the coefficient of the power of 2 because its coefficient is 2, and oxygen, and it doesn't have a power because its coefficient is 1. So now what I have is an equilibrium constant calculation, or my law of mass action for this particular reaction. And given some information about either the value of K or the value of concentrations of water, hydrogen, and or oxygen, I could figure out an unknown value. Now, when we get to solids, we actually omit them from our equilibrium expression because the concentration of a solid is constant. As I increase the amount of solid, I'm also increasing the moles and I'm increasing the volume by a proportional amount. And so since the concentration is constant, we exclude that from our equilibrium expression or our law of mass action. Now, when I look at the reaction below, I see I have a solid as a reactant, and I have 2 gases as the product. I can still write a law of mass action, but it's only going to include those non-solid substances. So here's an example. I have 2 carbon monoxide going to carbon dioxide plus carbon solid. In this case, my solid is one of my products, and I don't include that in the equilibrium expression. I write the concentration of CO2, again, no power because my coefficient is 1, over the concentration of carbon monoxide to the second power because my coefficient is 2. Note also that I've added a subscript here to the K value, and so C stands for concentration. Because one thing we're going to look at as we talk about equilibrium is the fact that we can talk about the equilibrium constant with respect to concentration or the equilibrium constant with respect to the pressure of any gases present. When we're dealing with gases, we can use either Kc or Kp. We do need to indicate which one we're calculating because the values can be different. The other thing I exclude from my law of mass action is for pure liquids. Again, just like with solids, the concentration of pure liquids does not change. So we have a reaction here, 2H2O2 going to oxygen and water, so the decomposition of hydrogen peroxide. And when I look at my law of mass action, I have my oxygen as a product. I notice that water, because it's a pure liquid, is omitted. On the bottom, I have H2O2 to the second power for the coefficient there, and note that this is aqueous. Remember that aqueous means it's dissolved in water, it's a solution, and so I do include that in my law of mass action. So the only thing I omit are solids and my pure liquids. Once I've assembled my law of mass action, I can use that information to calculate the equilibrium constant. Now, the value of that equilibrium constant can tell me something about whether products are favored or whether reactants are favored. If I have a value of K much greater than 1, one thing I can look at is to remember that I have products over reactants. And so if I have a value that's greater than 1, what that tells me is the concentration of the products is going to be much greater than the concentration of the reactants. I don't know how far the reaction is going to proceed to form products, but the fact that it's greater than 1 tells me I'm going to have more products than reactants present. The reverse is also true. When I look at a K value much less than 1, I can see that reactants are favored. Here, again, I have my products on the top, my reactants on the bottom, and if this number is much less than 1, that tells me the numerator is a much smaller number than the denominator, and therefore that shows that my reactants are going to be the predominant species, and what we see is that, in fact, we have a little bit of product forming here, but predominantly what's present in this mixture is the reactant. Now, every reaction has its own K value, and that can be affected by a variety of factors. What we're worried about right now is how can I set up the law of mass action? How can I calculate the value of K? So let's look at an example here. What is the law of mass action for the reaction of A to B? So you've had a chance to answer that question. Hopefully you saw that it should be answer B, where we have B over A, because B is our product, A is our reactant, and so we want to set our law of mass action up to indicate products over reactants. Because the reaction we're giving has coefficients of 1 for both substances, we do not need to include a power for either of those numbers. What we'll look at next is figuring out how we can take a law of mass action for multiple reactions and combine them all into one expression and get one value of K simply by knowing the law of mass actions and the K values for some individual reactions that make up that overall reaction.